Welcome everyone to Lecture 1, ROS Nodes, Topics and Tools. So, as part of your homework, and last week we were talking, one of the assignments was, what is ROS all about? So, in this first slide, let me introduce or motivate why we might want to use ROS. So, let's take this Baxter robot. It has 2 arms and 2 hands and several cameras, and those lights above the head are sonars that use sound waves to detect motion. And we want to be able to control all the different sensors and actuators available in the robot. So we might want to control the sonar, also the cameras, the graphical user interface screen. In the arms, we have joint torques. We want to be able to read them. Also the joint velocities or the joint angles, the joint states, and maybe have these as inputs to a controller that has a desired location. Within the movement of a robot, we want to do things like collision avoidance, and of course, we'll need to compute kinematics. If you're not familiar with kinematics, it's the transformation of a robot's arms, joint angles, to a Cartesian pose, an XYZ pose with the rotation at the hand or the end effector. On top of that, we might want to do a particular kind of path planning. We also need to control the grippers, whether they're electric grippers or vacuum grippers. If we have a force torque sensor, we would do that. And then, of course, any kind of higher level intelligence for the vision, for the arms, for the whole system, task planning, on and on and on. So if you are new to robotics, maybe you would create one single CPP file or maybe a few libraries and try to start developing code for all of this. And it's possible that you'd have very big centralized pieces of code with a lot of dependencies. So later in the future, if you want to change one part of the code, it's easy for the system to break or for you to have to change many other things. So the idea of having a architecture that is decentralized and also distributed came to become a central point in robotic middleware. And so that's one of the things that ROS is doing. It's separating what would be a really large, big piece of code into very small, focused pieces of code. And so this is in the spirit of object-oriented programming, where each function does one thing. So here we have one process that will do one thing, and they will communicate across each other. And this allows us to do many things. Of course, it's encapsulated, so there's just one thing per process. It's scalable. We can create programs that can grow in size and complexity, or it can also be smaller and more simple. And it's more fault tolerant. If one part breaks, the whole system doesn't have to break. But on top of that, other things that we might want to do with this robot is be able to visualize data. We have so much data coming in and out of this robot from the sensors and the actuators, and we want to be able to visualize what's happening with that. Even for simulation, we want to be able to see the robot model. We want to see where each of the links of the robot arms and the robot body and the robot head are all located, the hands. So data visualization is very important. We want to be able to simulate many things in robotics because it allows us to run things quicker. If they break, there's no damage to the physical robot. We can test different algorithms and get to see what they do much more easily than with the real robot. Debugging is something that's also very important, so we want to have easy to use tools to go into the code and see what's going on. system statistics, including looking at a graph of processes and how they're connected, how things are running, where we might have bottlenecks is also important. And we want to be able to see inside the network the bandwidth, the hertz, what's coming in and out of each process. And so all of these things can actually be put together in what is a middleware architecture. And that's what ROS is going to be able to provide for us, including simulations through Gazebo and other environments. And so all of this is really complicated to run just on conventional executable files and libraries. There's a few more layers that we need to make all of this complexity more manageable and easy for us to identify problems and strengths and weaknesses of the system. This is really what ROS is all about. It's a middleware. And yes, it's not the only one. There are others like OpenRTM from Japan, Oracles and YARP from Europe, and a few others. And so this is what we're going to be learning today. And we're going to be starting with the ROS network. So the core idea about ROS is that it's going to be a network. It uses XML RPC protocols to help different processes or nodes talk to each other. XML is a kind of language, and RPC is remote procedure calls based on TCP and UDP communications. And in today's lecture and the next lecture, we're going to be learning about topics, services, and actions. Topics are going to be data that is published and subscribed through our nodes, and they are characterized by being asynchronous. What does that mean? A node, like in this example, the talker, might start publishing information anytime that he wants, even if there's no listener available. And then the listener might connect whenever it wants, 1 second, 5, 10 seconds later, or it might even start listening before the talker even exists. So there is no concern for synchronicity. That means that information is going to be lost. And so using topics means you really don't care if some information is lost. Also, it's a many-to-many scheme, meaning that you might have 1, 2, or 3 or more nodes all subscribing to one talker or one publication. It doesn't matter. So this is a very flexible kind of communication scheme. The second one is going to be services. Services is a lot more focused. It's a synchronous and a one-to-many communication scheme. So you'll have a client and a server. We'll look at that in our next lecture, where the client has a very particular request from the server, and the server then replies with an answer. We might have one node that has several client calls to different servers, so it can be a one-to-many. Finally, the action lib is like a service but builds on top of it. It's ideal for long-duration tasks, and it allows you to get more information from that task, including goal information, status information, feedback information. And you can also have options of canceling a request and restarting a new one. So let's jump in and look a little bit more about the graph and ROS nodes. Take a look at this image. We have this dotted square here. This represents the ROS core environment. Anytime that we want to start ROS, we're going to type ROS core in the terminal, as I'll show you in a second. With the terminal, we're going to have a master, a ROS master, which keeps a list of all existing nodes. And this diagram, for example, we might have 4 nodes, 2 blue ones and 2 green ones. And these nodes will use topics for publication and subscription. The green colors might publish information. These might be sensors. For example, this would be a force torque sensor, and this might be the joint angle states. The blue nodes might be the subscribers, things that want to get information. Maybe you want to do some kind of classification task using machine learning for something, or you might have a PID controller that needs information like the goal states before it can move the robot arms or legs to a particular location. So these publication nodes then are going to publish topics, which are seen by these black arrows. In a sense, you can imagine a topic being like a road on the street. And on this road, you're going to have cars going through it. Cars may be these little packets of information that we call messages. Now, each topic has a particular descriptor. You can think of it as the name of a street. So, for example, the force torque sensor node might publish a topic called robot force torque sensor. And so this road or this topic will be described purely by this name. Then on each of these topics, we have data going through them, or in ROS language, we call it a message. The message also has a type. This can be understood perhaps as having different types of car on the road. This might be a Ford, this might be a Volvo, this might be a Chrysler car, anything like that. And so in ROS terminology, each of these messages also has a type. They are organized by libraries. For example, here might be a message that is typed geometry messages, and there's many kinds of geometry messages. This one might be a wrench stamped. We're going to be learning more about that later. So in general, this is how the graph is populated. You have nodes that either publish data or subscribe to data. Those that publish have topics with particular names and messages with particular types. The subscription nodes will talk to the ROS master to say, hey, please send to me information on this topic. The ROS master will find out where the publication node is for that topic, will connect these two nodes together, and then the subscriber will be able to, using the topic name, receive the specific data. In general, as we try to start writing ROS nodes, there's a few things we'll need to learn. First is how ROS is organized. In our computers, we'll have multiple packages or ROS packages. Each particular package, for example, can have multiple nodes. Say, for instance, you might have a package for force torque sensors or force torque data. So here you might have different nodes for different force torque sensors. Each force torque sensor might have slightly different specification, so you might need to have different nodes for each of the different sensors. A ROS package can have messages. These can be standard message types from ROS, or they can also be custom types that you create for your particular robot or need. The same is true for services and actions, where you create your own services or your own actions to meet the needs of some particular task. You can have also other scripts that might accomplish different things for you and launch files. For ROS, the basic processing unit, as we have just briefly mentioned, is going to be the node. Inside node, we have node handles, which are basically memory components that are going to allow us to create publications or subscriptions. We'll also, in nodes, we can have service client objects and service server objects that relay information through the service. The same is true for actions and then parameters. Finally, We also have tools for monitoring what's going on inside of a node. We have node tools, for example, they give us information about a specific node, what's the process ID, what does it publish to, what does it subscribe to, how many services does it have. We can also have tools that study not the nodes, but the topics that exist in the graph in general, and we might want to know what is the message type of a particular topic, what's the frequency of publication of a topic. We might want to know the bandwidth, how much memory or how much bandwidth it's using. We can also look at message tools to understand exactly what they look like, what kind of data is in a message type. We have service tools also to understand, for example, the request and the result of a service, and graphical tools to see the ROS graph, to plot data, to look at images, and a host of other things. So having said that, we're going to start introducing the basic ROS communication method, which is going to be the publish and subscribe methodology. So let us start then by making sure that we have a workspace where all packages will be created. This was part of the last lecture. So let's just open a terminal and take a look at what's going on in here. So remember that you can open a terminal just from this HUD display. I use Terminator. You can also open this with Control-Alt-Delete. And by following my instructions from last lecture, you should have this path created, ROS Indigo. And here we would have a workspace called ROS Workspace, right? And finally, we should have a folder called Source. Okay? And it's inside Source where we want to create all of our packages. Now, ROS has a tool called Catkin Create Package. This tool allows us to create a package with whatever name we give here. For example, my minimal nodes. And finally, we need to introduce a third set of arguments, which are dependencies. Dependencies is other pieces of code that a package might depend on. For example, if we want to use C++ and ROS, we need to use the ROS CPP library in order to write these packages. So this is another package that we might depend on. If we want to use a basic set of standard messages like sending ROS integers, ROS floats, ROS strings, then we might use a dependency like this. So if you want to create such a package, you could just say catkin create package my minimal nodes, and then introduce the dependencies, ROS CPP and standard messages. Here, the system then would say, hey, look, I've created this package, my minimal node, and I've included these files, cmakeLists.txt, package.xml, and include folder with the name of the package following my minimal nodes, and then also a source folder where all the CPP files will be located. Finally, it gives you the location, and then it recommends to adjust the values in the package XML for extra information. For every package, we have two files that are critical to distinguish that package from the others. The first one is a cmakeLists.txt. This file is used to manually modify which nodes we want to build. So if you create a new node, we need to go into this file and say, hey, I have a new node, and we need to compile it and link it this way. This file will use cat-can-make to build, compile, and link all the code that we have. Now, please make sure to look at the resources folder in the class website, where I have some very useful documents for you to be able to understand all the details about cat-can-make. We will still comment more in this lecture later, but for an in-depth, detailed description, you can look at the resources. And the second file is going to be package.xml. This is simply an information file. It's going to say what's the name of this package, who created it, what's their email, a basic description, and what are the build time and runtime dependencies of the file. So it'll say, hey, you're using ROS CPP, you're using standard messages, and a few other things. Okay, so we have a package, and we're interested in writing a ROS publisher node. And we'll see in a second how ROS publishers are called through the node handle class. And in this class, we're going to mainly be looking at C++ implementations of nodes, and sometimes at Python implementations of nodes. And each of these two languages has a specific ROS API library to facilitate the implementation of a node and its publications and subscriptions. You can click on each of these links to find more details about those implementations. Now, we'll look at code in a second, but just let me introduce it. When we create a publication node or a publication object, we'll need 2 or 3 arguments, depending whether we're using C++ or Python. These 2 or 3 arguments provide the following information. We first need to say, what is the type of the topic? All topics need a type. These are the message types. And so we need to assign a ROS message. From our previous example, we were using geometry messages range stamped. So we would say this topic is carrying this kind of message or this kind of data. We also need to give it a name, like the name of a road. So as we do that, we also will need to know that these names are going to be relative to something called the namespace. And I will give you a very concrete example a little bit later about this. I just wanted to introduce you to the idea of a namespace first. Finally, there's a third argument called the queue size. What is this? So as we publish, each node will have a particular speed at which it can publish. You can say, hey node, I want to publish 10 times per second, or 100 times per second, or 1,000 times per second, even 40,000 times per second. But the fact that your node is trying to do that doesn't always mean that all of that data can go through your Wi-Fi connection or your Ethernet connection. It depends how your network is doing. Those messages may go through or may not go through. So the interesting point is, what happens if my computer cannot handle the speed? For example, what happens if you say, yeah, I want to send 40,000 messages a second, but your computer can only process, say, 1,000 messages per second? That means that every second you'd be losing 39,000 messages. So this queue size is a little vector or queue that would save messages that are not yet sent, but you don't want to lose them. So this means I really don't want to lose this information. If you click on these links, you'll get a little bit of more advice on what the queue size might be for different situations. For now, we will just keep this number to 0. Okay, if you have properly installed the code in the book, we're going to be able to change to this directory, Learning ROS Part 1, Minimal Nodes source file. Within this location, we're going to be able to find a CPP file called minimal publisher. Now you can open this file using gedit if you're feeling not so familiar with Emacs, but if you want to venture, you can also open Emacs, open this file with Emacs, and this little sign, in English we call it the ampersand, and it helps us to separate Emacs from the terminal. So for example, let's go back over here, and let me find that. So here's the Learning ROS folder, wherever it is, and we will go to part 1 by doing CD, and then we will go here to minimal notes. Notice how I can just press tab and the entire package will appear quickly. If you cannot do this, it means your terminal or your system is not yet finding ROS packages. Then we will go into the source folder, and you can see that we have all of these files right here, minimalpublisher.cpp. So let me open this. You can use Emacs or Vim or gedit or your favorite text editor. And so this is now opening this window. I can zoom in like this, and I'll be coming back to this file just in a second. As a summary of what this file is going to do is we have the following. Number 1, we're going to have some ROS headers that are going to allow us to interact with the code and C++. Then we're going to initialize this node. This is very important. This is the step in which the node gets registered with the ROS master and gets a space in the graph. And ROS master says, hey, I have a node here. This is the name, and this is where it lives. And then later, we will create a node handle. This is an important object that will allow us to create a publisher object. We'll create the publisher object, and we'll call a method called advertise. Now advertise, the goal of advertise is to go back to the ROS master and say, ROS master, I have a topic, I want to register with you. And I'm going to give you the name, and I'm going to give you the type, and please keep that information in your database. And so then the ROS master takes that information, builds a table for that node about the topics it wants to publish, and anytime later that a subscriber wants to receive information from that topic, then ROS master knows where that topic is located. And finally, in the code, we will begin to publish that information to the network. Okay, so let's go over here to the code and take a look. You can also include some numbers. I can't see them clearly here. So let's look at these two headers. The first one is #include ROS/ROS.h. This is going to introduce the API for ROS with C++. We call that ROS CPP to allow us to be able to have this ROS namespace and then allow us to call different methods from that namespace like init, and also to access different ROS types like node handle and publisher as such. Okay, that's what ROS.h is doing. The second #include has to do with the definition of a message type. So here we're going to be publishing just some float 64s, but they're not standard float 64s. They belong to the library of standard messages in ROS. So if you have properly installed ROS in your computer, you'll be able to access this message type. The header file provides all the definitions, and this would be saved in the OPT file. For example, we can cd to OPT ROS Indigo, and here you would find the include folder. And here we can go into standard messages. And here we can go to look at the definition for a float 64. A quick way to do that is by just using less. And this is a rather large file, but you would find the definition of this type that is standard for ROS, okay? All right, so we then have this main function. We can have a number of arguments from the command line. This is useful when we run a node from the command line and we want to control something through the arguments. Okay, next line, we have ROS init. This is the very first thing we do anytime we create a ROS node. It takes these three arguments, argc, argv, and then this name right here. This name is a string, and this can be anything that you want, but this is going to be the default name that this node will have when it is run. So when you run this, the graph, the ROS graph, or the ROS master will look at this node and say, oh, the name of this node is minimal publisher. And this is a default name. This default name can be changed later on in something called the launch file, or even in the command line, but this is just the default name. Okay, you will always do that. The second thing that you do is create a node handle object. Here we're just going to call it n, but you can actually call it whatever you want. nh, x, it doesn't matter. N is just an easy variable to use for node handle. Okay, and then we have this third line where we want to create an object of type ROS publisher. So in this case, we're going to say, let's create this object, my publisher object. And it's going to be of type ROS publisher. Now we need to give this object a particular value. How do we do that? We take the node handle, and then we call the advertise method on that. Okay? And for advertising, we're going to talk to the ROS master and say, hey, look, I have a topic, and the name of that topic is going to be called topic1. It's a string. And then I just want to make sure you know the topic type, and it's going to be a standard message, float 64. These curly brackets here, angled brackets, sorry, refer to a templated type. That means that this advertise method actually can be of many types, not just this one. It can be standard messages int, standard messages string, geometry messages wrench or wrench stamped. Actually, this will be able to take any type that you want. And then we'll just accumulate one message on the buffer here for now. Okay, so now we have a publisher object. What we want to do now is create our data, which is going to be a standard message float 64, and we're going to call that input float. And then we want to populate that data or change it based on some particular robot task. For now, we're just going to demonstrate a basic behavior. So we'll say, hey, let's take this input float variable and access its data type and set the value equal to 0. This data type might be confusing to you. So I'll make this point again in the slides later, but let me mention one thing for you right now. If I open a terminal, there's a command called ROS message. And this ROS message is going to help me to analyze different messages that exist in my computer in the ROS ecosystem. So you have a tool called show to see what's going on inside of a ROS message. So you might be able to say, hey, I want to see or show me what standard messages float 64 looks like. So you might start typing ROS standard messages, double tap here, and then you get a long list of alternatives. And so you might be able to look at, oh, where's float 64? Here it is. So let me type that in, float 64, and press enter. When I press enter, it just shows me this one line. It says, hey, look, this ROS standard messages float 64 type has one element inside of it called data, and it's of type float64. This is where you can save the actual data. So this is a little bit different from regular C++, where you would just expect to say input float equals 0.0. Here we have a structure, and it has one element inside, also of type float64, and it's called data, so we can access and assign the value in this way. Okay, so now something that is very typical for a ROS node or a ROS publisher is to create a while loop. This while loop will run over and over again, and it will have some kind of action inside, and then this is where we want to actually do the publication of the data. Now, if you notice inside of this while loop, we have one argument. Maybe in your experience, you might put a number 1 in here just to keep the while loop running. But ROS has this method called OK. And what this means, or what this does, is it keeps the while loop running until the node crashes. That can either happen by some exception or by having a user press Control-C on their keyboard. And this can also send a system flag to the system in order to kill the application. And this is one way to exit a node in ROS. So all that we're doing in this particular example is taking input float data and add a very small number to it, 0.001. Okay, and so every time we go through the loop, the information of the data element in the structure will be increasing. The next thing we want to do is actually publish that to the network. So we take the myPublisher object that we created up here, and this object, which is of the ROS publisher type, has one method called publish. And this publish will take a message. In this case, it's the input float message that we created right here and the data which we have affected right here. So as soon as this command gets executed, it'll send the message data through the topic out into the network. Okay? And one question I have for you is, how fast do you think this loop will run? Now let's close this for a second and let me go back to the presentation. Once we have this code, we want to be able to compile it and run it. This is because it's C++ code. So anytime we have a new node, at least we'll have new lines in the CMake lists file, and we'll need to add 2 components. The first one is we want to create an executable. Okay, we want to tell the system, hey, what is the relative path relative to our package? What's the relative path of the CPP? So in this case, for example, it might be right here. It's in the source folder of the package, and it has this name, minimalpublisher.cpp. And we also want to give the executable a desired name. And this is the name of the node. the name of the file node, as I'll show you in a second. And here we're calling this my minimal publisher. This is different from the name that we use in the init method when we run the node. I'll show you that in a second. So you would have this kind of line, add executable, name of the file, name of the executable, and then its relative path. If I go back here to this window, I might say, hey, let me go to minimal nodes quickly, and I have the CMake lists text here. This Emacs N will not work in your computer. It's a shortcut that I have here that I want to show you real quick. So I might have this catkin CMake lists file, sorry, and I'll go down a little bit to this section where we say, let's declare a CPP executable. So this is where you would manually, for example, enter this command, add executable, give the name, minimal publisher, and then the relative path. The second thing we want to do is to define with what files the executable needs to link with. So many times when we have include files at the top of our C++ file, it means we want to call methods from another library. So here is where we select what libraries we need to link with. Now by default, this will always happen. We need to link with catkin libraries. What is catkin libraries? Well, catkin libraries will contain all the ROS dependencies for things like ROS CPP or ROS Python, or even some dependencies for messages. Okay, and so how do we do that in the cmake lists.txt file? We would use this command, target link libraries, put the name of our node, our executable node, and then we have this variable. In cmake, variables are created with this money sign and then curly brackets here and here, and then a predefined environment variable. And this catkin libraries is designed and created earlier in the file, and it's kind of done freely for us. We don't worry about this. So if I come back here, you'll see immediately that after add execute, we might have target link libraries, the name of the node, and then this variable here for catkin libraries. Okay, so once we do that, we need to compile. And so I have a question for you. Before you run catkin make, as I introduced last week, we need to be in a particular location. Do you remember what folder location is necessary before making or compiling the code? So could I do it here? No, you're right. We can't do it here. We need to be able to go to the top of our workspace. Our workspace is here, ROS workspace. So we need to go back to this level. Here we have IAM 1, 2, 3, 4, 5, 6 levels down from the workspace. Now it'll be different for you. You can just type pwd to look at your present working directory and then go here. So I could just do this, 2, 3, 4, 5, 6, and then be in my ROS workspace. Another thing you could do is just do this, ROS Indigo ROS workspace. That would also take you to that location. And it is here that you could just run catkin make to build that package. Now, for me, I have many packages here, so it would take some while to run. So let me go back to the presentation while that is going on. Let me make a few notes on catkin make for your information. Catkin make is built on top of cmake. Cmake is another technology that allows us to compile code in a more efficient way. So given that catkin make is built on top of cmake, we can use cmake flags for many things, in particular to make specific packages or change the build type. Let me give you these two examples. Sometimes you might be interested to debug a process or debug some code. If that is true, we need to set the build type to debug. So you might say something like this. Let's do catkin make space -d. This means I'm going to give you a flag and then give the particular flag. cmake build type equals, and then the kind of type that you want to build. It can be debug, it can be release for optimized code, and a few other options. Another useful flag for cmake is or that we can use for catkin actually, is making a single package. So let's say that you have 100 packages in your workspace, but you don't want to build all of them. That might be time consuming. Let's say you only want to build a package that you changed, in this case, minimal nodes. So if you want to do that, you can say, let me give you another flag, -d, and then catkin whitelist packages equals minimal nodes. Okay, in this case, everything worked fine, but if I just want to make the minimal nodes, I can do this. I can just type a few letters and press tab, and then try to correctly write down that node. And this would be able to finish more quickly. So you can see here it says it's traversing minimal nodes, it's compiling the code up to 100%, and then finally linking all of my nodes with ROS CPP or catkin dependencies. Great. So as you see, catkin make uses information from cmake lists.txt to specify all the build rules for a particular directory. And catkin make is designed by ROS as a specific build tool. It's very important to learn how it works. And we must always call catkin make from the top of the workspace. In our case, that's going to be the ROS workspace. When we finish running catkin make, we want to know where the executables and the include files are located. Executable files are always going to be placed in this location: ROS workspace, development folder, lib. Let's take a look at that. Clear the screen, make a listing, and you'll see here that we have the development folder. Now I have more folders and more things here than you do, but all you need to worry about is, do I have the development folder? So you can then change into that directory and see that you have another set of folders like include and lib. And if you go inside lib, you'll have a lot of executables, and the one we're interested right now is minimal nodes. In my case, you can easily find it here. And the file that we just created is this one, minimal publisher. And this is the code that I showed you earlier that will do the work of running the publication code. Okay. The include files are placed under development include. Let's go to that one right here. And what the include file has would be for minimal nodes. We also have to go into there. Let me see this. For this case, actually, we won't have anything specific because standard messages is part of the standard ROS architecture. But any custom message that you create would be located here. And in the near future, you'll see how that is important for us. Okay? So we were here. So finally, a little summary. Did you know that catkin make builds on top of cmake, but also that cmake builds on top of make, and in turn that make builds on top of G++ and GCC? All of these are very interesting, and I will put some resources for you on the class website if you're interested in learning more about cmake, make, and G++. A little bit more information about the cmake lists file. This is the first time we're looking at it. This may be a little bit of advanced information. You can simply consider this slide to be for reference. Let me go back to that cmake lists file. Okay, if you look at the top of this file, you'll very quickly see that we have this keyword or command find package. So find package is going to look for specific ROS files like ROS CPP and standard messages. And it's going to generate some cmake variables that are necessary in order to be able to have the API that we use later to call methods from these libraries. So if ROS EPP is used as a specific package, then this find package command would create the ROS EPP include directories and the ROS EPP library directories. Then we have this second thing, catkin required, that you see right here. What does that do? Well, catkin required loads specific catkin CMake macros that are used for ROS. That is basically saying, hey, CMake, I'm actually using catkin, so we're going to do things a little bit different, and these are the macros you need to know what to do for that. Okay, so just enabling some functionality for catkin itself. Finally, we have this catkin package right here, down here. And right now we have nothing in there, but catkin package will change how CMake builds code. It creates executables in the development folder, and it will also generate this very important file, development setup.bash, which is very useful to source a workspace. Let's take a look at that. If I go to the top of the workspace, right here to ROS workspace, you can do that quickly. If your workspace environment variable is set up, you can quickly just type ROS-cd and you will do that. Then we can go inside of development, and here we have the setup.bash file, which we can source in a particular terminal to be able to access the code related to this workspace. This, of course, is done in the bashrc file as well in order for all terminals to be able to do that. So if I want to see the bashrc file, and I come down here for, let me see, where do I have that? Right here for my workspace, I can say source, give the full path, ROS workspace, development, setup.bash. That will ensure that every time I open a new window like this one or like this one, all of these will be able to find any packages in that workspace. If you cannot quickly move to a package like this, it means that something has not been installed correctly. Feel free to connect with me through the QQ group, and I'll be happy to assist you throughout the week. This source command takes the setup.bash file and ensures that a particular terminal can load those files. Okay, and the setup.bash file has all the necessary environment variables for the workspace and the system to be able to run code properly. One thing that we had to do last week is to source the ROS setup. So for example, this will automatically be done for me because my environment is already set up, but I can say source opt ROS indigo setup.bash. And that makes sure that ROS is able to run in this window. And I can check by running the env command in Linux. Now env will load all kinds of variables. It's a really long list. So one thing that we can do is run env with a pipe. A pipe is run like this, and it takes two commands. One might be env, and the other one might be a function like grep that takes one parameter, one string parameter like ROS root. What grep does, it's looking at a particular list of files and looking for this string. Now, so what the pipe is doing, it says, let's take this output, which was the long list that I showed you before, and use it as an input to this function. So grep actually needs two arguments: the string that you want to look for, and then the list of files, which is provided by env. So when I do that, actually, I only get back one result. It says from that long list of files or paths that or variables that env provided me with, there's only one line that matches ROS root, and it is located at this path location. So this means that actually the system can find ROS because of the way that we sourced it. So we know that it works. And, we can also do that for the workspace. So we looked from the bashrc file that we have a ROS workspace. Let me show you here one more time. This ROS workspace, so we say export this environment variable and provide the path to your ROS workspace. When you do that, we can also do something like this. What did I do wrong? What did I do wrong? Where's my workspace? Sorry. Let me load this one more time and try that again. Here it is. ROS workspace, and we have this path. So then when I do ROS CD, it automatically takes me to the same path as well. Okay, so all of this sourcing is important in order for your computer, first, to be able to find ROS, second, to be able to find your workspace. And even further, it's not on the slides, but if you want to know what packages are found in your computer, you can use a command called ROSPack. And we can use ROSPack, let me see. We can use ROSPack profile to go through our workspace and print to us what packages are available. So we could say ROSPack profile. Okay, and this will give you a long list of packages or locations of where packages might be located. And if you add zombie only, you can see a longer list of details. Sorry, let me do that one more time. Minimize a little bit the size of this. So here we can find a lot of packages located in my workspace. For you, this list will be a lot smaller. Okay? I can even pipe this with grep, with minimal. I didn't see this minute. I cannot see this one. I'm making a little mistake here, but ROSPack profile zombie only will show you basically all of the packages that you have installed. Okay, now we have compiled this publisher. We want to learn how to run it. It's taking us a long time to get here, but now we're ready to get started. And there are two ways to start ROS. The first one is manually typing ROS core onto a terminal, and the second one is using a ROS launch file, which we'll learn a little bit later in the class. So let's go back to this terminal, and you just have to write ROS core. So here it says, hey, I'm going to log all the information from this session to this file. Great. And then checking log directory for disk usage, just making sure you don't have too much information that is clogging your system. And then it says, hey, look, I started the ROS launch server. This is the ROS master. It'll be located in this version, in this location. And then we get a summary of the system. It says, hey, I have two parameters. One is called ROS distro, set to Indigo, and ROS version set to 1.11.21. Then it gives you a summary of the nodes. It says auto starting the new master. This master has a PID, a process identification number like this one. And the node process is at this address. And then there's a second process called ROS out, which I haven't yet introduced, but it's another process for logging information. It has a PID information. And now we know that ROS is running. Okay? So ROS core number 1 starts the ROS master. It also starts something called a parameter server that will be handling parameter information from different nodes. And it also starts a bunch of logging capabilities for debugging the network. Now, once we have started ROS, we want to run a node. And to run the node, we can use a ROS tool called ROS run. ROS run will take 2 arguments. Number 1 is a package name. Remember that one package can have more than one node. So first we give a package name, and second we give the desired node name. This is the name that we included in the CMake lists file in order that we can find it. So let's go back over here, and I can just type Control-Shift-O to open a second window down here, and I can say ROS run, what's my package name? Minimal nodes. And here, what is the name that I created in the CMake lists file? Minimal, yeah, that's right, minimal publisher. Yeah. If you don't remember, let me go there real quick to show you. ROS CD, minimal nodes, and then I can show you Emacs CMake lists, and I can just quickly find publisher, which is right here. We gave this number, this name to that executable, minimal publisher. That's why we're using this name here. Okay, so we press enter, and, well, nothing's showing up, but actually the node is running. Yep, here's the commands. And the next question is, well, how do we know that the node is running? And now we're going to begin to learn something about the ROS node tool. Yep, so let me clear this window and type ROS node -H. The -H for any tool will always give you a little bit of information about what you can do with that tool. Let me shrink this window. Everything is still there. And let me also shrink this window a little bit. So we have ROS node, and you can do things like list and info, even machine. List will say, hey, what are all the nodes that are running? Info might give you more information about one particular node. Machine might tell you, hey, what is the machine from which that node is running? And then you can even kill a node using this tool function here. So we can say ROS node list, and it says, hey, there's two nodes running right now in ROS. One is this logging node that we saw earlier, and the second one is this minimal publisher. So even though we don't see anything happening here, there is actually one node running. And if we say ROS node info and then provide the name of that node, it will say, hey, this node called minimal publisher is publishing the following things. Topic 1, and topic 1 has a type of standard messages float 64, which is what we did in the CPP file. And then this is about logging information, so we'll skip that for now. Nothing about subscriptions, services, something about logging that is done by default, and we don't need to worry about that. And then this node exists at this location in the server graph and has this PID information. And the topic 1 topic is going outbound, and it's using TCP protocol to send that information out. Okay, so we're getting a lot of information there, and then if we want to look at how the graph, the ROS graph, looks visually, we can use RQT graph. Click on this link for more information. So we can just run that by saying ROS run RQT graph, RQT graph. In this case, we're using that command. This is the package name. This is the node name. We'll wait for a second. Depending on the speed of your computer, you will get this graph sooner or later. So here, what we're doing is we're looking at the name of this node as minimal publisher with a topic inside that is sending information out. And over here, we can click on different options to either simplify or make the visualization of the network more complex. Because this is very simple, nothing much changes here. We have the minimal publisher, and actually this one is the graph, the graphical user interface of the graph. And both of them are also publishing some logging information out to the ROS out node. Okay, so RQT graph can be really interesting to be able to see what's going on in that graph. I'll close that. Now, I want to introduce something about node handles and namespaces, which is going to be very important for you to understand, especially down the line. Node handles may or may not have a namespace. Namespace is an idea from programming languages used to differentiate possibly similar function names across programs. So right now we're calling this node minimal nodes. Could you imagine the possibility of having another code that might be interested in calling their node the same way, minimal nodes? Well, this might be something that can happen easily. For example, if you have a robot with two arms, maybe you have the right arm, maybe you have the left arm, maybe you have a node that is called force torque sensor. Okay, so, but both arms may have a force torque sensor, and maybe you thought, hey, I should give this name to both of them. So that might be confusing. So in that case, you might want to create a namespace that differentiates that particular node name. So for one, it might be like right, and then force torque sensor, and for the other one might be left and force torque sensor. What we're going to do right now is just to demonstrate how the node handle and the namespace are connected is go back to our C++ code and change the publisher code by adding a string to the constructor of the node handle. Yep, so we'll go to this line where this was empty before, I think, and then we'll call this minimal nodes here. And that will be a namespace. So let me kill this. We can leave ROS core running. And then we can go to minimal nodes, to the source folder. Look at how I did that in just one line. And then I can open my minimal publisher. Oh, in fact, sorry about that. This change has been implemented already. Sorry, let me run this one more time so you can see that. Let me introduce also this topic called ROS topic. Here we have oh, sorry. So here we have our topic 1. It just appears as shown here, topic 1. And my fault, I have not added this namespace to the node handle, which is down here. So let's go here to the creation of the node handle, add 2 parentheses, 2 quotes, and then type minimal nodes. Okay, so this might be a namespace that you use to distinguish this particular topic. So I will save that and close it. the next thing that I need to do, so the next thing I need to do is make or compile that node. And after I do that and run the code, when we do ROS topic list, you will see this description for the topic. Okay, so let's go ahead and go to the top of the workspace, right here, run cat can make. Let's just do that package, minimal nodes, so we don't have to do a lot of it. We build it, we link it, and then back to this window. Let me kill what we have there, run it one more time. Now that it's running, I can also run ROS topic list one more time, and look, the way that the topic is published is different. It now has this namespace, which was created when we did this to the node handle. And then let me introduce you to one more thing that's interesting, which is called topic remapping. Let's say we have a subscriber, and the subscriber just wants to talk to topic 1, not to minimal nodes topic 1, okay? If we do that, then I need to know that this node, minimal publisher, is publishing a topic with this name, minimal nodes topic 1. But if I want to change that topic to topic 1, I can remap it like this. I say ROS run, package name, minimal nodes, node name, minimal publisher, original topic name, minimal nodes topic 1, and then colon equals, and then a new name like this. So if we go back over here and I kill this node, now I can just type minimal nodes topic 1 colon equals topic 1. Okay, press enter, that is running, and when I do the ROS topic list again, that appears as topic 1. So this is just one way of changing the name of a topic on the command line. This can also be done in a launch file later. We will look at that at a later time today. Okay, so this is just some things that we can do related to node handles, namespaces, and topic remappings. Hope that is not too confusing, but we will keep touching these ideas in the future, okay? Now for now, let me, okay, we'll just keep this like this for now. Here's a quick slide about ROS topic commands. I have shown some of these commands briefly by looking at the listing of active topics here. But we have other things that are very interesting, like the frequency or the rate of the topic, or if I want to see what message is being printed by that topic, or if I want to look at the bandwidth of that topic, or if I want to look at the message type of that topic. Further, even if I want to manually publish by myself to something, I can look at pub. So let's look at a few of those right now. So we have this running. Let me take this window away. We have this node running, and we can say, hey, ROS topic hertz, topic 1, and it shows me the speed at which this node is running, 46,724 times per second. Now I have a really fast computer, so we get this really high number. You might experience a much smaller number than this, but this is giving us the average rate per second or the frequency of that topic. We can also say bandwidth, how much data it's being used per second. In this case, 642 kilobytes. So it's a really low amount of data. But if you're working with images or larger data structures, this number could be a lot higher. And depending on your Wi-Fi speed and your Wi-Fi bandwidth, you may want to pay attention to this number, especially if you're doing critical safety tasks like navigation or real-time manipulation. Okay? If I want to know what's being published inside of this, we can use echo. Remember that we were just adding 0.001 data to the base number of 0. And so right now we're running this at 46,000 times per second, and so that number is just growing really, really fast. Here we're at 344,000 right now, and that number is getting added very quickly. Now also notice that this value is associated to data, which is the internal element of the standard messages float 64 structure. Okay, and one last thing I'll just show you is this pub type. So ROS topic pub. If you don't know how to use this command, again, you can always use the handy -h flag to know how to do that. So here, ROS topic pub will say, hey, give me a topic name wherever you want to publish, and give me the type, and then give me the data or the arguments. Okay? So let's say we want to do ROS topic pub, and we'll choose just a topic 2, and we can say standard messages float 64, and then the arguments parts is a little bit tricky. We can come down here, we insert this single quotes, then these 2 curly brackets, and then we need to access the data element that we want to use. In this case, it might be data, and then a colon, which is similar to an equal sign, followed by a space, and then any value that you want. So in this case, let's say 10.5. So when I do that, I am publishing this message. Okay, let me kill this from the top, and I can say ROS topic list. Now I see topic 2 here, and if I want to see what's inside topic 2, ROS topic echo, sorry, topic 2, I am getting this number. Now, we haven't discussed anything about the rate at which this topic 2 is being published. We see here that we have a rate flag or option in which we can set the rate in hertz. So let's say we want to run this topic at a rate of 100 times per second. So you can do something like that. And then all of a sudden, let me make this a full screen. This is running 100 times per second. I could check that just by looking at hertz like this. And you can see that the system is telling us that, yeah, that's very, very close to 100 times per second. Okay? So that's some of the tools for ROS topic. Okay, did you know? Remember that you can use -h to get some extra information. And you can also do Linux pipes on these commands to get something more interesting. Let's say you want to get the message type in a topic. What can we do? We could say ROS topic type for this topic, and then ROS message show. Let's see how that works together. So right here, if I say ROS topic type topic 2, that says, hey, you have a standard messages float 64. But if I want to see what that message looks like, I can open my pipe here, then just say ROS message show, and this is as if I was copying this standard messages float 64 string here and putting it over here so that I can see what's inside of that data. So here it tells me, hey, this has the data element and it's of type float 64. So hope you can enjoy that and learn to use pipes to get extra information from your tools. Okay, so you saw, let's talk about scheduling node timing, controlling how fast a node runs or how fast it publishes. In our previous publisher, ROS topic hertz, showed us that the node was publishing in my computer at 47 hertz. But you know, a more reasonable update would be 1 kilohertz or 500 hertz. The ROS library has a time class and a rate class, both for C++ and Python, that can help control the publication rates. So anytime that we want to set the node frequency, we need to use two steps. The first one is simply to create a rate object. And this object needs the frequency that we want to publish with as part of the constructor input. So this might look like this: ROS rate, the object name, whatever you want to use here, and then a frequency. The second step then would be to call the sleep function inside the while loop. For example, object name.sleep. To demonstrate this, we can go back to minimal nodes and to the source folder, and you'll see that here we have a sleepy minimal publisher. Okay, so we can open that one. Let me make this a full screen, and you'll notice that we are creating a ROS rate object called nap time, and we are passing a frequency of 1 time per second to the constructor. This object is normally going to be created outside the while loop, and then this while loop, the frequency of the while loop can be controlled by calling naptime.sleep in this manner. After you do something like that, remember that you would want to compile and build this new node, and then create the executable. If we do that, then we can say ROS run minimal nodes sleepy minimal publisher, and here we can say, hey, let me see what's the ROS topic list. Here we have topic 1, so then show me the frequency. And right now we just have 1 time per second. Okay, so then if we say ROS topic echo topic 1, we'll see that this data is very slowly incrementing, just once per second. Great. So hopefully this has been useful for you to learn about scheduling the node timing. Okay. Now, here's one more tool I want to introduce to you to open a file very quickly. It's called the ROS-ed tool. Now, ROS-ed uses a variable set in the bashrc file. That variable name is called editor. And so in our bashrc file, we need to say, hey, I want to create this variable name editor. So we say export editor, and then you can give it the name of your favorite text editor. It can be Vim, it can be gedit, it can be Emacs, or it can be, in my case, Emacs with no new window. Okay, so very quickly, let's look at that. I can say bashrc, and I'll just search very quickly for editor. And so you see that here in my file I have export editor equals Emacs NW. Anytime you change your bashrc file, make sure you source it to load the latest changes. And so when I do that, then I can use ROS-ed in the following way. You have the package name, for example, minimal nodes, and then the name of a file within that package that you want to open. So it can be ROS-ed, minimal nodes, and anything else after that. Sleepy, minimal publisher.cpp, and bam, here is the code, and you can see that it's so fast to open these files, and this is really useful when your ROS workspace grows and grows and grows, and you have hundreds of packages inside. Emacs gives you a great flexibility, as does Vim, so I recommend learning these text editors very, very much, even though they might be difficult to learn at the beginning. In the same way, I can open the CMake lists file for this package very quickly. and I can quickly switch to other things from within this window, like the package.xml. So very, very useful tool. Okay. Now, we've learned how to do the publisher. We can now move on how to write the raw subscriber. And the raw subscriber is going to be a little bit more challenging, and for now we just introduce the simplest case, and a little bit later we discuss more advanced situations. Let me provide you an overview. First, raw subscribers are going to be implemented or called through the node handle class, just like we did for the publishers. As before, we have specific implementations for ROS CPP and ROS Python. Subscribers usually require 3 arguments, right? It's a node that says, hey, I want to get this data. So you need to know the topic type. What kind of data is going to be coming to me? I need to know the topic name. And then we have something which is the callback function. The callback function will have a name, so I need to provide that. And this is the function that will process the data that comes in. So as soon as you get one piece of data, the callback is called and the data is processed there. Callbacks are really a critical component of ROS. And callbacks can be called in different ways. And so please go ahead and click on this link, callbacks and spinning, on the slides, and go and spend some very good time studying all the possibilities, which I will also introduce here, but just for extra reference. Then in the ROS GitHub, there's a lot of examples for callbacks and spinning. And so I also want to ask you to review those for your homework. Oops. So let's look a little bit more at the details. We know that earlier we created a topic called topic 1. So we want to subscribe to topic 1. Okay. We also want to have the right topic type. And if we're using C++, the topic type can be defined within the callback function. Where in the callback function? Specifically in the input variable type. So let's say we have a function called myCallback. It returns void, and it takes one argument, which we're going to call message holder. We're going to look at that type, and here, for example, we see standard messages float 64. We pass this as reference, so we don't make extra copies, and we set the const keyword here so that we indicate that actually we don't want to change this incoming data. We just want to read it and use it. If we use ROS Pi, we have something similar, but still a slightly different prototype. So here we might say ROS Pi subscriber, topic name, here would be topic 1. Here we would have float 64, and then the name of a callback, myCallback, or just in this case, callback like this. Okay, now remember that callback is the name of the function that we're going to call when the data becomes available. This callback can be either a global class or a class method, which is private. For now, in our current example, we're going to look at a global class. And in C++, this particularly works through something called boostbind. You can click here for more details. Actually, before I continue to look at this slide, let me open the subscriber and minimal nodes so you can take a look at it. Okay. So what I want to introduce to you here is the following. Here we have the headers, ros.h, float64.h, similar to our publisher. And immediately we have this global function that is declared and defined right here under the name of myCallback. It only takes one input variable called message holder, and it's of type standard messages float 64. There's only one thing we're going to do with this piece of data here in a second, and it's going to be to print out to the screen the value of the messages. So we're going to use a macro called ROS info, which is exactly like cout, but better, because it's optimized not to clog down the network. And so here it works like fprintf in C++. So we can say received value is with a specificator here, and then passing the data, in this case message holder.data. Then we have main, we have init as before, we call this minimal subscriber, we have our node handle, and then we create a subscriber object like we did with the publisher. So we have raw subscriber with the name, and we assign the following value. I want to subscribe to topic 1. I'm only going to also have a queue of 1 in case I miss anything, and I want to connect to this callback called my callback. Okay? Then we have this command spin that I want to introduce now here. Spin is something that is going to be very critical to understand, and sometimes can be a little bit difficult to process at the beginning. In general, there are going to be 4 types of spin calls that we can make. And what spin does is, for each callback, it's going to create a table with a buffer of calls depending on what data has been published. Now, spin calls can be blocking or non-blocking. Blocking means that once you call spin, you never exit that call. It's a little bit like saying while one and never exiting. We'll look at details in a second. Non-blocking means that you make a single function call and then return back to your place of execution. Spin calls can also be single-threaded or multi-threaded. Multi-threaded gives you higher performance if you have multiple callbacks, and I'll introduce that in a second. Most of the time we will use non-blocking calls, okay? And so here is a summary of those 4 methods. We have raw spin, spin once, multi-threaded spin, and asynchronous multi-threaded spin. Sorry, no G here. Spin by itself is blocking, single-threaded. Spin once, non-blocking, single-threaded. And as you might just guess, multi-threaded spin, blocking multi-threaded, and asynchronous multi-threaded spin is non-blocking multi-threaded. So we've looked at this code. We see that we are using standard messages float 64. And ROS info is a set of logging macros in ROS. Click here for more details that will print to screen, and you'll see how this works in just a moment. Okay, ROS info is part of ROS console. It's a very efficient way of logging data in a distributed network. It works like fprintf and C++, but it's more efficient. And we also have variants of that like ROS info stream. This one works more like cout. And we have other kinds of macros that will only publish information in different settings, like when you're debugging, these may show up, or anytime you want to show a warning when something is getting serious, you can use you can say ROS warn. Or even when something crashes, you can use ROS error to print error messages to the screen. Okay, so now let me just illustrate a little bit more about callbacks and spins, and a little bit about threads and blocking. Consider a scenario where you have a subscriber node and it's talking to 2 topics. Topic 1 and topic 2. Well, if we have spin here, what this will do is um, have a call to the callback connected to topic 1 as soon as this data message comes into the node. And then if topic 2 data message comes in, then this table would insert this callback function corresponding to topic 2. And then if this data message comes in after that, you'd have a new entry on this table to make a call to the callback for topic 1. And as more data comes in, more functions get appended. Okay, so spin is creating this table with a buffer of callbacks according to the order in which incoming messages are taking place. So this might be spin or spin once. And if we have spin, we're just looping. Now, if no data is coming in, there would be no callbacks here, but we would still not be able to exit the spin call because it's blocking. If we do spin once, we might execute this callback one time, return to our execution position in the main loop, and when that main loop finishes, we might revisit here topic 2. As part of your homework, I'll invite you to study the differences between spin and spin once. In the case where we have multi-threaded callbacks, what we're doing is we're creating independent tables for independent topics. And so you could see that this would be a little bit more efficient, or much more efficient, as we could process both callbacks in parallel. Okay? When might you be interested in doing multi-threaded callbacks? When you have more than one subscription, and maybe if your system cannot process the callbacks fast enough. Okay. So we have this minimal subscriber in our system, and we want to run that. I think this is not my minimal subscriber. I'm sorry, this is just minimal subscriber. I will fix that in the slides later. So here we have ROS core from before, and we can run this subscriber by saying ROS run minimal nodes, minimal subscriber. Now I didn't show you, but of course this is in the CMake lists file and minimal nodes. So if I look here, we have the add executable. Minimal subscriber is going to be the name of the executable, and this is the relative path. We have done catkin make. So if I go into development and lib and minimal nodes, I should be able to find that minimal subscriber right here. In fact, when we do ROS run minimal nodes, minimal subscriber, what this is really doing is coming to this location and just running the minimal subscriber. In fact, for more advanced cases, you could also run the subscriber locally in this way if you wish. I won't do that right now, but I did want to mention that to you. So when I press enter, the subscriber is running. Now, nothing is getting shown in this terminal. Can you guess why? Let's look at the number of ROS nodes running. And we see that, well, actually we just have a subscriber running, but no publisher. As before, we can also run the RQT graph. And for this node, we have some shortcuts from the system. We can just type RQT graph directly and open the window like this. Again, we only see one node right here. So now let's try to run the publisher together. ROS run minimal publisher, minimal nodes, minimal publisher. This will be much more interesting. As soon as we do this, oh, by the way, I forgot that we changed the topic name. Let's run the sleepy publisher. let me do that from the beginning. ROS run, minimal nodes, sleepy minimal publisher. And so here, the subscriber is saying, hey, I received a value of this. This is from the callback, remember? And we can refresh the graph right here. We can say, let's fit it. So now we have this minimal publisher 2 that is sending out the data over topic 1, and it's incoming here into the minimal subscriber. Okay, so that's very interesting to see that. We can also say ROS nodes list. We can see that we have these 2 nodes. We can also say ROS topic list, where we have this topic 1. And we can also say, give me all the information about this topic. It's saying, hey, it's being published by minimal publisher 2, and it's being subscribed to by minimal subscriber. Okay, so I just want you to be able to connect all the dots here. And remember that what we are seeing on this screen is just what was typed for ROS info. Received value is %f to get the float, and that's what we're doing. And this is the rate of 1 hertz per second. Now, if I kill the publisher, immediately the subscriber stops publishing. Let me go back to my minimal publisher, and remember that when I do this, I get nothing because the topic name is different. See, here we change the node space, the namespace, sorry, to minimal nodes topic 1. So right now, the minimal subscriber is looking for a subscription to topic 1. And right now this topic 1 does not exist, so it doesn't know the type. I can correct that, as we saw before, by changing, remapping the topic. So here we had minimal nodes, topic 1, and we can just change that to topic 1. Oh, I have made a mistake here. Let me do that again. Topic 1. Let me see. I'm making a mistake here. ROS run, minimal nodes, minimal publisher. Let's look at that again. So we use this to remap. Copy and paste over here. Equals topic 1. Okay. As soon as we do that properly, we remap the topic properly, then we can see that the subscriber now is getting this at a very high rate of 46 kilohertz. Okay, so this is how the publisher and the subscriber work together. It's this talking and listening that works together. We need the same topic name, we need the same topic type, and then we can get this kind of communication. Okay, and now I'm going to talk about another ROS tool called Catkin Simple. Catkin Simple is a package that simplifies Catkin Make considerably. Okay, our book has code for a script that can create packages using Catkin Simple. That means that when we create a package, the cmakeLists.txt file will be slightly modified to use catkin simple. The first thing that we need to do to use this tool is to create an alias in the bash RC file. What is an alias? An alias is simply a shortcut. We will want to use a command like cs create package for catkin simple, and we need to provide the path of a Python script that would be probably in this location, quotes, tilde or username, folder path, ROS Indigo, ROS workspace, and my source folder, in my case, books, Newman, which you probably don't have, and then just learning ROS external packages, cs create package.py. Just to illustrate, let me close these windows for now. I can come over here to minimal nodes, maybe go up one level, 2 levels. This is an external packages, 1 more level. So here learning ROS and external packages, and here we have this script cs create package pi. Okay, so in the bash RC file, we would find a location for aliases. You'll see that there's quite a bunch of them by default, but here I have a section for the ones that I create manually. And so I would say alias cs create package, and then that full path for your computer right here. Remember to source the bash RC file to activate any changes, and then we're going to use this to create packages with catkin simple. Okay, so let me go back here. Let's say let's create one package called my minimal nodes 2. Sorry. Which I have already created, but let me remove it. So here I might use my new tool, cs create package, my minimal nodes 2, along with the dependencies as before. Yep, so now we have this folder, and we have package XML and cmake lists.txt. Let's take a look at that cmakes list in a second. So in this case, for example, it will simplify the way we compile and build a node. Instead of using the command add executable, here we're going to use catkin simple add executable, pass the name of the node we want, and then the relative path. And by doing this, we don't have to have the extra line of target link that we had in the regular catkin make. So as you can see, there's a declaration for catkin simple. We don't have things in find package anymore. And here in cs add executable, all we would do here then is say minimal publisher 3 source minimal publisher, like that. Yep. And so from here we can go to the top of our workspace, say catkin make, flag the catkin whitelist packages minimal nodes, and you can see the way we ran. Now let's go over into the development folder, lib minimal nodes, Oh, we didn't see the third one here. 1 second. Sorry, I'm back. I noticed I made a mistake. The first one is, let's go to the first one is I wasn't using the correct package. Sorry about that interruption. We changed to my minimal nodes. Okay, and if we look into the source folder, there's nothing in there. Actually, we need to copy the minimal publisher from the other package. So we can say, hey, let's copy that. We need to go up 2 levels, and then let's see. Oh, we need to get the right location. So here we are in my computer. Books. So I have a long path to go here, but then I can find this minimal publisher.cpp and copy it right here. Okay, so once I have that, then I can go back to the top of the workspace and call cat-can-make, but this time with the new name for the package, my minimal nodes 2. Oh, found a little mistake with the name of the publisher, and it still cannot find minimal publisher here. That's okay. Sometimes we'll have this kind of problems. So let's go to my minimal nodes 2, and let's look at that CMake lists file. See what I wrote down. Source minimal publisher.cpp. Let me change this name. Let's see if I don't have a copy of that before. Cannot find source file. Oh, I still didn't copy that properly. What did I do? Let me get this location. Let me do the copy a different way. Copy minimal publisher CPP to this location. Okay, it's here. Let me try that. So let me go to the top of the workspace and try that one more time with the idea of my minimal nodes 2. In this case, it builds properly, it links, so I can go into the development folder, into the lib folder, and then into my minimal nodes 2, and then find that minimal publisher for here. So actually, sorry for that confusion. We had to copy over the minimal publisher.cpp to the right source folder in the new package, and then make it. But as you can see from the CMake lists.txt file, we just needed 1 line instead of 2 to build that node, and then we didn't need to worry about other things. So it can really simplify things. Great. Another tool we want to learn is going to be launch files. Sometimes if we want to launch multiple files at the same time, we can use something called the launch file. Launch files are always saved in a launch folder inside of a package. If we go back to minimal nodes, you'll see right here that we have a launch folder. Okay? Launch files, when they're run, can automatically start ROS core. To do that, we use the ROS launch command. The ROS launch command would use the package name and then the name of a launch file. In our case, I'll introduce you to minimalnodes.launch in a second. Okay? And the way that this launch file looks is as follows. It uses XML notation, and XML has always beginning and ending tags defined by starting and closing angled brackets, where the terminal statement uses a /. So here would say launch and finish launch. We want to run two nodes, the publisher and the subscriber. Now, in this element, we can say node as a keyword, and we need to provide three things: the name of the node for the graph, the package name, and the executable name. Okay, so let me clarify these for a second. So here in package, we can do minimal nodes or my minimal nodes 2 or any package name that we want. Then this type is the actual name of the executable. So here we have sleepy minimal publisher or minimal subscriber. Okay, and then we have the name that we want the node to have in the graph. Remember that we gave a default name with ROS init. If we don't provide this name here, then that node would automatically have the default name. But it is at this place in the launch file where we can change that name if we prefer. Again, imagine that you have the right arm and the left arm of a robot, and you have code to publish the force torque sensor data. And so you just call it force torque sensor. In this place, you might have a launch file for the right arm and another one for the left arm. And here you could say right force torque sensor, left force torque sensor. So it's a way to customize the names of the nodes. If I want to see what's inside of this one, we can open it up. And so here I have the package minimal nodes, and then sleepy minimal publisher and minimal subscriber. Okay. So I'll close, let me see, close this. What am I doing? Okay. So if I want to run that, I have nothing here. Now we don't need to say ROS core anymore. Here we can just say ROS launch, minimal nodes as the package, minimal nodes dot launch. When we do that, we see that the publisher and the subscriber are run here together. So if we do ROS node list, we see we have a publisher and a subscriber. Now look at the names of these nodes. Where do they come from? They come from this launch file that we used here with just publisher and subscriber. A little bit different from the default names that we used before. If we do ROS topic list, we see that topic 1 is here. And if we do the graph, you'll also see that we have the publisher and the subscriber right here. One thing that you'll notice though is that there's no data being published onto the screen as before. Hopefully you noticed that, and there's a reason for that. In launch files, we have something called XML tags. And by the way, those files always need a .launch extension. And these tags, we can provide different functionality to our launch files. By clicking on this link, you can learn more about such functionality. We can use node tags for nodes, param tags for parameters, arg tags for arguments, include tags for including launch files inside launch files, group tags in case where we want to provide a specific namespace or remapping for a node. We can do remap to change topics by using this notation from one topic to another topic. But if we want to print out information on the screen, we can come back to this ROS launch file. And for the subscriber, I can add one command called screen, and then set that equal to output. Okay. Actually, let me open this link real quick so you can see a little bit more of these tags. Here it comes. Where are my tags? So here you can learn many elements. I'm missing the screen output that I want to show you. Here in tag reference, you can see a little bit more in the way that some of the nodes are started. I'm looking for the screen output. This parameters, we won't see it here. Sorry, the one I wanted to show you is not directly on this link, but it's okay. So come back to this part. We say screen equals output, save that file, and then we can launch it again. Oh, I made a mistake here. It's the other way around. That's why I was hesitating. It should be probably output equals screen. And so it's output equals screen. And now you can see that the subscriber node is able to print its information onto the screen. The reason we have this tag in launch files is because we have many nodes, and sometimes it can be very confusing if we print information from all the nodes at the same time. So this gives us another degree of control over the things that we want to show on the terminal. Okay, great. One more thing, if we want to debug C++, and this is something that I want to introduce really early on in the class because it's going to be very useful for you, we need to do a couple of things. In Linux, debugging really takes place with GDB. Okay, DB stands for debugging, and it is helpful to debug anything that is C or C++ executables or libraries. Now, before we can debug, we need to set the build type of a package to debug, as we saw on slide 10. Okay, so for example, we could go back to the top of the workspace and run catkin make and say I want a flag, and this is CMake build type. Okay, And here we say debug, and this might set the debug type for all of our packages. Okay. So we have this. We can see, for example, here in my minimal nodes 2, that we've been doing this. You can even add another flag for specific packages if you don't want to build the whole thing. Catkin whitelist packages. You can also do these two things in conjunction. Okay, so we would be doing this for those packages as well. So now let's say that you want to run the subscriber first. So you might do a manual ROS core, then you might do a ROS run, minimal nodes, minimal subscriber. Okay, so you have that running. But you want to run the publisher under debug mode. So the simplest form is to run GDB on the executable found in the development minimal nodes folder. Okay, so we could do something like this: GDB, ROS workspace, development, lib, minimal nodes, minimal publisher. Okay, and let me show you what that looks like. Let me maybe open a vertical window on this side. Actually, let me run it on this side. So we go to the top of the workspace, go inside development, lib, minimal nodes, and here we have the minimal publisher. And right now, this should have a debug symbols so that we can debug it. The way we can know that is by running GDB on this. We see this final statement: reading symbols from minimal publisher done. Now, if you've never used GDB before, please look at the resources I'm attaching to the presentation. But you can also type help for beginning to explore different things. For example, this is some basic groups of categories. So for example, we'd say help running. Yeah. And here, for example, start is the way you start running a debugged program. Run the debugged program until the beginning of the main procedure. Okay? You could also say help start to look at those details. There's other keywords like help break. This will set a breakpoint at a specified line or a specified function. So here you could say help main or help line 22. Okay. Another thing we could do is list. This lists a specified function or line, but when we don't include any arguments, it'll show us the first 10 lines of code. Okay, we can clear the screen with Control L. Let me make it a little bit smaller, and they say list again. So this shows me, since I called it a second time, it shows me 11 through 20. But I can also say, hey, show me lists from lines 1 to 10, like this. Or I can say, show me the code from 1 to 20, like this. The fact that I can show the code already says that I can access the code. Okay? So I can maybe click start on here, and it'll say, hey, we have started debugging, and we are at breakpoint 1 at function main, and it gives you the value of any existing variables like argc equals 1, and this is the value of argv, we can dereference that to look at that information. So now if I want to go, the idea is we're here at line 4, we want to go line by line to see what is happening. For example, after line 20, once we go into the while loop, that would be most interesting. I can type next to move to the following line. So right now we have executed ROS init, and now we're going to create ROS node handle. Instead of typing next, I can also type N. And when this node handle is created, actually 4 threads are opened, but we won't discuss why that happens. But we can also now begin to examine the value of N. We can use print as a key command to see what's going inside of N. So here, for example, this node handle will say it has a namespace called minimal nodes. And so far there's no callback queue, and everything is working fine. Clear the screen, go to the next line. Yeah, and so we executed line 10. If you don't remember what that looks like, we can come back here. And we have the publisher object. So again, here we might want to look at what that looks like. You can also just tab on that. And this would give you a hard to read set of informations here. If you know more about C++, you could try to access the substructures of the variable. So for example, by looking at this px value, right now it says we have a shared pointer, and then there's some information there. We could also try to dereference this, where you get another address, and you can try to dereference that again. Oh, not in this way, I apologize. We can also access pn and then pi underscore, where you get more complex information about the publisher. This will not be immediately useful for you, but I just want to give you an example of how we might be able to debug something like this. So now we are currently in line 11, where we're going to create the input float. So we can say next, and next on this, and then print. We can also just do a P4 shortcut and type in input float, where we see, hey, we have a structure and there's an element called data equal to 0. Again, I could just access that and immediately get that value. Now, we're about to enter a while loop. So here we might just want to put a breakpoint on this line 24. To do that, we can type break or just B for short, and then the line number 24. And then instead of saying next here, we can use continue or C for short in order to move to the next breakpoint. Okay? So this immediately takes us to line 24, and here we can try to see what is the value of this data at different iterations. If I do continue, it's going to move me through the loop again, and so I can then look at this value one more time and see that it has incremented. Now, the breakpoint I placed on line 24 is breakpoint number 2. If I want to remove it, I can say delete 2, and now if I just say break, it'll give, delete 3. I was expecting a list of the breaks, but that is not it. If I have removed that break, if I just say continue, it is running around the loop, and then that value would have been larger. Let's try that one more time. Minimal publisher, just run start and continue without any breaks. And we don't see anything over here on minimal subscriber because we changed that namespace from before. If we do sleepy minimal publisher, we will see something print on this side. Now, instead of saying start, because start stops at the main loop, we can do run, and run won't stop in main. It will just continue until it finds a breakpoint. And in this case, we have not inserted any. So it'll run through the while loop consistently, and then the subscriber can receive that information. So this is one way of running GDB. The interface is not nice, but I want you to be able to understand how debugging takes place at the lowest level. This kind of knowledge and the ability to master this technique is critical to be able to understand and debug complex programs. At a later time, I might show you how to debug similarly through Emacs or other graphical user interfaces. Now I can stop a GDB with Control-C and use Q for quit, and also kill my subscriber and my ROS core over here. Okay? And certainly there are many other IDEs for ROS. You can interface with Emacs, with Vim, with Qt, with NetBeans, Eclipse, and there's a pretty new IDE called RoboWare developed here in China that provides really nice functionality specifically to ROS. The Qt plugin also is very nice, and both of these are under heavy development. I would encourage you to first understand how creating packages, creating launch files, editing the CMake lists text file works, and how debugging works before you use an IDE, so that you have a solid grasp of the low-level details of ROS and the Linux system, and then you can use this at a later time to save you time on those further edits. There's also the ability to debug in Python. I won't go into detail for that, but I do want to show you a basic overview of this. There's a program called PDB, or an extended version of that, IPDB, that is useful to debug Python scripts. You can say sudo apt-get install python IPDB to get that code or that binary. And then when you have a particular Python code, you can say import IPDB, and then in a given line, you can say IPDB.setTrace wherever you want to stop, and it'll work very similarly to GDB as I just showed you. Also for Python, you can use a standard Python editor or the more rich IPython, and other IDEs like Spider or PyCharm. Debugging can also be done inside launch files. Again, I won't go into details right now, but I do want to tell you that it can be done. You can use GDB, IPDB, memory leak, Valgrind software, all inside launch files. We will normally use arguments inside nodes to turn debugging on and off. This is a really nice ability to have. And it needs to be used with if and unless fields and a launch prefix field, where it might look something like this. I would create an argument called debug, set it to false by default. but then say if the user in the command line sets debug to true, then create an argument called GDB argument, and then run a new terminal with GDB on it and pass any command line arguments to it. Okay, so the unless is if that is not the case, then we have nothing here. But then in your node you might have minimal debug, minimal nodes, minimal publisher, and then here you have launch prefix with the value of GDB arg. And so if you say debug equals true, then this term would come right here and a new terminal would start. This would be the way to launch with a command argument for a launch file or even for a node. Debug colon equals with your value, in this case a Boolean, true or false. And finally, one more tool to introduce to you is ROS bags. They allow you to record and also play topic data. This is going to be extremely useful for debugging complex systems or saving time when you want to run something and just analyze the data. ROS bag allows you to choose what topics to save. Today we just have a node with one topic, but there are going to be times where you might be working with 10, 20, 30, 40, 50 topics at a time, and this will allow you to choose which ones, which data do you want to save. This creates a bag file, sorry, not gap, but bag, where the topics are recorded with timestamps. And ROS bag will save the files by default in the current directory. In fact, let me come here and we can say something like ROS bag help. And so here you can see that we can play a ROS bag or we can record a ROS bag. For more details on recording, the usage is ROS bag record and then any number of given topics, along with other functions. For example, the name with which you want to save that file, or a maximum duration for a bag file, or a maximum size for a bag file. In the same way, we can also choose how to play it in different ways. ROS bag play with a pause, where you can start it at a later time by pressing the space key, or you can use a particular frequency to publish the clock, or you can ask it to loop over and over again in case you want to see data around the clock, or you can select specific topics from the whole set of topics as well. When we want to record data, we can always finish the recording by pressing Control-C. Okay, so here we can then play the data and check any results through RQT console or RQT graph. So here's an example of how we can do this. Let's bring this over here. Let me open a few windows. So let's start ROS core at the bottom. Let's do a ROS run, minimal nodes, minimal publisher. Let's do the sleepy version. Okay, so we know that we have these topics, and so here we can say ROS bag record topic 1. Sorry, I wrote that wrong. Okay, so now we're subscribing to this topic and we are recording with this particular name. So we can let that run for some time and then kill it with Control-C and then play this one more time using ROS bag play. By the way, this is it just recorded it to the local directory with this name. So you could maybe copy it. And here, for example, we can say ROS topic echo topic 1. Right now it's running because we are running this node. Let me kill it. Yeah, this time there's nothing here, but if I say ROS bag play bag file, you can see that we get the time and the duration. And then here in the echo, we can get this data. We just ran for 12 seconds, and so we got this data so far. We can also do that with a loop. Okay, so this would go up to 12 and then start again. So you can see how that data is going up, 26, 30, and then start again from 18. Okay, so as you can see, this is very, very useful, especially when the system is more complex. This concludes our presentation for today. We went through details on how to publish, how to subscribe, the meaning of node handles and namespaces, as well as callbacks and spin cycles, and how we can integrate that into launch files, and further just looking at different tools that let us look inside the network and its performance, and finally how to record and play some of that data. Chapter 1 has a 4th section, which is a very practical section. This homework 2 will basically walk you through section 1.4. You can even skip reading section 1.4 and just directly read the homework, because the homework is primarily a repetition of section 1.4. It will help you to make sure you've downloaded and compiled minimal nodes and analyzed their performance. And later it introduces you to 2 new nodes, the simulator node, the controller node, mimicking a very simplistic way in which a robot might behave. And for your homework, you have to do some analysis on these 2 new nodes. So it will test your knowledge about ROS tools, like ROS node list, ROS topic, and even ROS plot and ROS graph. ROS plot we didn't look at so far, but it will be introduced in the homework. I hope you're excited. This will be a long homework, but I also think that you will find it very useful in helping you master the basics of nodes, topics, publication, and subscription. Next week, we will start learning about other kinds of communication like ROS services and actions. Thank you very much.